What if I told you that if just one part of the Golden Gate Bridge disappeared, the massive suspension cables, the entire bridge would collapse in seconds? The truth is, this landmark isn't just beautiful. It's one of the boldest pieces of engineering ever attempted, and today, I'll show you how it was built, why it still stands strong, and the crazy risks the engineers took to make it real. Respected Infinital community, hope you're all doing well. Buckle up, because this video will not only blow your mind, it will make you see the Golden Gate Bridge like never before. Why build it like this? The Golden Gate Strait is one of the most dangerous places to build a bridge. The waters are cold, the currents are violent, the fog is thick, and the winds can knock you sideways. On top of that, the gap between the two coastlines is about 2.7 kilometers. For 1930s engineers, this was almost madness. So why did Joseph Strauss, the chief engineer, choose a suspension bridge? Well, picture the options. A beam bridge would need dozens of piers built into the seabed. That means working 300 feet underwater, in deadly currents, impossible and insanely expensive. An arch bridge. That would have to rise to ridiculous heights, just to clear the shipping lane. Too complicated. The suspension design was the answer, with only two massive towers and cables that carried the weight. Ships could pass freely, costs were reduced, and the bridge could finally stretch across that brutal gap. The hidden forces. Here's where things get interesting. The main suspension cables don't just hang there. They are under unimaginable tension. Imagine thousands of tons pulling on them non-stop. That force doesn't vanish. It pushes into the towers. If nothing was done, those towers would bend inward and collapse. The solution? Extend the cables to giant concrete anchorages buried in the hills. Those anchor blocks hold the cables tight, canceling out the inward pull. Strauss even optimized the placement by moving the towers slightly closer together. Engineers reduced tension in the cables, which meant thinner cables and lower costs. It's engineering efficiency at its finest. The deck and its secret skeleton. Now, let's talk about the roadway. The part where cars and people actually cross. If they had just attached the cables directly to a concrete road deck, the bridge would have failed in no time. Why? Because concrete is strong when you press it, but weak when you pull it. Cracks would form. Strauss had a smarter idea. He used a massive steel truss beneath the road deck. The suspenders connected steel to steel, making the system strong and flexible. Only then was the concrete roadway placed on top. The road deck was made wide, about 27 meters, to prepare for future traffic demands. And to build it all, workers had to fight constant fog and wind. Prefabricated pieces were shipped in, lifted with derricks, and joined with rivets. Safety nets stretched under the deck saved dozens of workers' lives. Step by step, the steel skeleton grew. Finally, the whole bridge was painted a color now famous worldwide, international orange, bold, bright, and perfect against San Francisco's fog. The heat problem. But what happens when steel and concrete expand and shrink with temperature? If the bridge had been built as one solid piece, hot days would have cracked it apart. Strauss designed 7 separate sections connected with special finger expansion joints. These huge steel teeth could slide back and forth, allowing the deck to grow or shrink by nearly 4 feet in extreme weather. Smaller joints were also added every 50 feet to deal with micro-expansion. That's why even today, if you look closely, you'll see the deck breathing with the temperature, stretching in summer, contracting in winter, all without breaking. How tall is tall enough? The towers of the Golden Gate rise about 746 feet above the water. But why that number? Here's the trick. The angle of the suspension cables matters. If the towers were too short, the cables would be nearly flat, and the tension would skyrocket. If they were too tall, the cost would be unbearable. Through calculation, and experiments, Strauss found the sweet spot tall enough to reduce tension, short enough to be practical. The result: towers that remain iconic to this day, perfectly balanced between strength and economy, fighting the ocean for foundations. If building above the water was tough, the nightmare was what happened below. The North Tower sat on shallow ground, manageable enough, but the South Tower, that had to be planted in the middle of the Pacific's fury. Divers had to go 50 feet beneath the seabed to find hard rock. Explosives, blasted boulders, and debris was cleared underwater. Then came the brilliant move: fender walls. Massive concrete barriers were built to shield the foundation from the crushing waves. On top of that, engineers poured a reinforced concrete slab that acted like a lid. Workers tunneled underneath it, safe from currents, while the whole structure slowly sank under its own weight until it reached solid bedrock. From there, the foundation was poured, and the tower rose. Piece by piece, steel cells were stacked like Lego blocks, riveted into place until the towers pierced the sky, spinning the giant cables. The Golden Gate's cables are legends. From a distance, they look like two solid pipes. In reality, each cable is made of 27,000 individual steel wires bound together. If stretched out, the total length of those wires would circle the Earth more than 3 times. How did they build them? Workers first stretched pilot wires across the bay using spinning wheels. Then, strand after strand of steel wire was pulled over the towers, compacted, and clamped. Slowly, the bundle grew into a massive cable, thicker than a person is tall. At the ends, the cables were anchored deep into concrete blocks set in bedrock. Vertical suspenders were attached, and finally, the steel truss deck was hung beneath. The 50th anniversary test. Here's the story that proves just how well it all worked. On the bridge's 50th anniversary, about 300,000 people crowded onto the deck at the same time. That kind of load was never expected. The bridge sagged nearly 2 meters, and the towers bent inward slightly. People were scared, but the engineers smiled. That's exactly what suspension bridges are meant to do: bend, flex, absorb, and survive. Even under that insane weight, the Golden Gate held strong. Why it still stands today. The Golden Gate is more than just a pretty landmark. It's a system of solutions. Suspension span to keep ships moving, anchorages to stop tower collapse, steel truss to handle the deck loads, expansion, joints to let the bridge breathe, fender walls and deep foundations to fight the ocean, perfectly calculated tower height to reduce tension, cable system designed to take punishment. Every challenge had an answer. And that's why, nearly 90 years later, the bridge still stands as strong as ever. The Golden Gate Bridge isn't just a crossing. It's proof of human determination and creativity. It shows that with enough vision and problems, even the most impossible obstacles can be conquered. It's not just steel and concrete stretched across water. It's a living equation of strength, movement, and resilience. So next time you see the Golden Gate rising out of the fog, remember this: every cable, every bolt, every joint carries a story of risk, challenge, and brilliance. If this video opened your eyes to the genius behind this world wonder, hit like, share it with someone curious, and subscribe to the Infinital for more incredible stories from history's greatest creations. See you in the next one.